The late June sun beat down on Yokosuka Naval Air Technical Arsenal as a team of engineers gathered around the captured American fighter. They'd been waiting for this moment since the F6F Hellcat had arrived from Saipan 2 weeks earlier. Now, finally, the preliminary documentation was complete, and they could begin the real work. The work that might explain why Japan was losing the air war. Chief Engineer Nakamura gave the signal, and his team began removing the cowling panels. Each aluminum section came away carefully, meticulously, revealing more of what lay beneath. When the last panel lifted free, several engineers simply stopped and stared. The Pratt and Whitney R-two 1800 Double Wasp sat before them like some mechanical deity. 18 cylinders arranged in 2 rows, each cylinder head finned and massive, the entire assembly dominating the Hellcat's forward fuselage. The engine's sheer physical presence was overwhelming. This wasn't just larger than Japanese engines. It was fundamentally different, built to a scale that seemed almost wasteful, almost arrogant in its use of materials and mass. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Nakamura walked around the exposed engine slowly, running calculations in his head. He'd read the preliminary specifications, but seeing the actual hardware made those numbers real in a way that reports never could. Someone handed him the weight documentation, 2,360 pounds, the engine alone. He looked across the hangar at the Mitsubishi A6M0 sitting in the corner, awaiting its own maintenance. That entire aircraft, empty, weighed 3,700 pounds. The Americans had built a single engine that weighed nearly 2/3 as much as Japan's frontline fighter. And this engine produced 2,000 horsepower. The implications cascaded through his mind like a collapsing building. Every pound of that engine's mass represented capability, represented American industrial confidence, represented an approach to aviation warfare that Japan had either misunderstood or chosen to ignore. The Zero's Nakajima Sakai 12 engine, sitting in that fighter across the hangar, displaced 27.9 litres and produced 1,130 horsepower. It was a magnificent piece of engineering, a triumph of efficiency and careful design. It had terrorized Allied pilots in 1941 and 1942, and it was completely outclassed. The R2800 displaced 46 litres and produced nearly twice the power. The American engine wasn't just bigger, it was extracting more power per litre of displacement, which meant the Americans had solved problems Japanese engineers were still struggling with. Higher compression ratios, better supercharging, more sophisticated cooling, more reliable, high-output operation. Nakamura's assistant, Lieutenant Suzuki, spoke quietly beside him. How did they build this? The manufacturing precision alone? That's exactly the question, Nakamura replied. Not just how they designed it, how they manufactured it, how they manufacture hundreds of them, thousands of them. The engineers began their preliminary external examination. Every surface of the engine told a story. The cylinder head castings showed evidence of precision work that required machinery Japan's bombed-out factories no longer possessed. The crankcase was a massive casting, thick-walled and robust. The push rods, valve springs, and rocker assemblies all spoke to an engineering philosophy that prioritized reliability and sustained high-power output over minimizing weight. One of the younger engineers measured the cylinder bore with calipers. 5.75 inches, he called out. Someone else measured the stroke. 6 inches. Nakamura did the calculation. Each cylinder displaced 155.9 cubic inches. Multiply by 18 cylinders. 2,804 cubic inches total, nearly 46 litres. The Sakai's 27.9 litres seemed almost delicate by comparison, but understanding the engine's size was just the beginning. The real questions lay deeper. How did it achieve such high power output reliably? What materials composed those cylinder heads? How did the cooling system manage the tremendous heat of high compression combustion? What manufacturing processes created components to such tight tolerances? How did the supercharger maintain manifold pressure across such a wide altitude range? And perhaps most importantly, could Japan build anything to match it? Nakamura already suspected the answer to that last question, but he kept his thoughts to himself. His job was to analyze the engine, document everything, understand it completely. The strategic implications, the uncomfortable truths about Japan's industrial capacity, those would come later. For now, they had work to do. Begin detailed disassembly, he ordered. Photograph everything. Measure everything. I want to understand every design decision these Americans made. But to understand why this engine mattered so desperately, why its capture represented one of the most important intelligence coups of the Pacific War, you had to go back 3 weeks earlier. Back to Saipan. Back to the moment when Japanese ground crews spotted something in the tall grass near Aslito airfield that made them forget the artillery fire raining down around them. An intact American fighter, the fighter that was killing them by the hundreds. And inside its cowling, hidden beneath aluminum panels, sat the mechanical heart that had changed the balance of power in the Pacific sky. The monster they now needed to understand. The tropical heat shimmered over Aslito airfield on Saipan in mid-June of 1944 as American forces pushed steadily inland. The airfield had changed hands twice already in the savage fighting for the island, and Japanese defenders knew it wouldn't be theirs much longer. Artillery fire walked across the cratered runways in irregular patterns. The shattered remains of hangars smouldered. Wrecked aircraft littered the field like broken toys. Sergeant Takeshi Yamamoto led a small ground crew through the chaos, searching for anything salvageable. Intact fuel tanks, working radios, anything that might help keep the remaining Japanese aircraft flying for another day. They'd almost walked past it before Yamamoto noticed the shape in the tall grass near the perimeter. An F6F Hellcat, American, relatively intact, sitting there as if it had simply decided to take a rest. Yamamoto stopped so abruptly that the man behind him nearly collided with him. There, he pointed. The other crew members followed his gaze, and for a moment they forgot about the incoming artillery. Forgot about the battle raging across the island. Forgot about everything except what they were looking at. This wasn't wreckage. This was an opportunity. For nearly 2 years, Japanese pilots had been sending back increasingly desperate reports about the Hellcat. The fighter had appeared in combat in August of 1943, and within months, it had fundamentally altered the balance of air power in the Pacific. Pilots described an aircraft that could climb away from a zero effortlessly, that could dive to speeds where pursuit became suicidal, that could absorb damage that would obliterate Japanese fighters and keep flying. But combat reports, filtered through the chaos of air battles and the trauma of survivors, weren't engineering data. They couldn't tell you why the Hellcat could do these things. They couldn't explain the technical solutions that made such performance possible. Here, sitting in the grass, was something infinitely more valuable than combat intelligence. Here was actual aircraft, and somewhere inside that cowling sat the engine Japanese pilots feared most. Yamamoto's mind raced through priorities. The Americans would counterattack within hours, possibly minutes. They needed to move the fighter immediately, but more importantly, they needed to preserve it, particularly the engine. Everything else, the airframe, the guns, the systems, all of that was secondary to what sat behind those cowling panels. "Get the truck," Yamamoto ordered. "Carefully. We damaged that engine, and this is worthless." The recovery operation began immediately. Ground crews worked under intermittent artillery fire, their movements quick and efficient despite the danger. They couldn't fly the Hellcat out. Fuel was too scarce, and even if they could get it running, the runway was too damaged. They'd have to move it by truck to a more secure location, then prepare it for transport to the mainland. The irony wasn't lost on anyone. This engine, This piece of American engineering might represent Japan's last chance to understand exactly what they were up against. Combat reports from the previous week's air battles had been catastrophic. On June 19th, in the battle that American pilots would later call the Great Marianas Turkey Shoot, Japan had lost approximately 300 aircraft in a single day. The Hellcat had been the primary weapon in that slaughter. 300 aircraft, 300 trained pilots. Losses Japan couldn't replace. And the fighter responsible sat here, intact, waiting to give up its secrets. The ground crew worked with desperate efficiency. They disconnected the propeller carefully, mindful that the engine's reduction gearbox was a critical component they'd need to study. They drained fluids, tagged every disconnected line and cable, documented the position of every control. The Hellcat had to reach Japan as complete as possible. By late afternoon, with American forces clearly visible advancing across the Rizaftan airfield's western perimeter, the fighter was ready for transport. The engine had been their first priority throughout the operation. They'd built a special cradle for the cowling section, packed it with salvaged cushioning material, and secured it separately from the rest of the fuselage. If they lost everything else in transit, if the ship carrying the Hellcat took damage, if any disaster befell them, the engine had to survive. That engine represented more than mechanical components. It was a window into American industrial capability, a chance to understand how they produced such reliable high-power output, an opportunity to discover what materials, what manufacturing techniques, what design philosophies made the R2800 Double Wasp possible. Yamamoto watched the truck pull away, carrying its precious cargo toward the harbour. Artillery fire was increasing now. The Americans would have the airfield by nightfall, but the Hellcat was already on its way to Japan. By late June, as Saipan fell completely to American control, the captured Hellcat was already en route to the Japanese mainland. It arrived at Yokosuka Naval Air Technical Arsenal on a grey morning, partially disassembled for transport, but with all major components intact. The recovery team had done remarkable work under impossible conditions. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Engineers waited at the dock as the cargo was offloaded. They'd been preparing for this moment since receiving word of the capture. Workspaces had been cleared, measurement equipment had been calibrated, photography stations had been set up. They'd assembled some of Japan's finest aeronautical minds, all waiting to examine the fighter that was systematically destroying Japanese naval aviation. As the crates were carried into the hangar, Chief Engineer Nakamura stood watching. He'd seen the preliminary specifications in intelligence reports: 2,000 horsepower, 18 cylinders, 46 litres displacement. The numbers seemed almost impossible, but in a few days they'd begin disassembly, and those numbers would transform from specifications on paper into hard, measurable reality. The final crate, the one containing the cowling section and its precious contents, was handled with extraordinary care. 4 men carried it, moving slowly, setting it down gently in the prepared workspace. Soon they'd open it. Soon they'd see what 2,000 American horses looked like when engineered into metal and forged into the most successful carrier fighter of the war. Show us what's under that cowling, Nakamura thought. Show us what we're really fighting against. The disassembly of the R2800 Double Wasp began on the 1st of July, 1944. Chief Engineer Nakamura had spent the previous week establishing protocols for the teardown. Every step, it would be photographed. Every component would be measured, weighed, and documented before removal. Every material would be analysed. They might never get another chance to examine an intact example of the engine that was deciding the outcome of the Pacific Air War. The photographic team set up their equipment around the engine. Flash bulbs, multiple camera angles, close-up lenses for detailed shots of individual components. The first photographs captured the engine in its fully assembled state, exactly as it had arrived from Saipan. Then the real work began. The cylinder heads came off first, 18 of them, one for each cylinder, arranged in 2 rows around the massive crankcase. Each head was a complex casting, incorporating intake and exhaust ports, valve seats, spark plug bosses, and cooling fins. Lieutenant Suzuki measured the first head carefully. The intake valve diameter was larger than he'd expected. The exhaust valve showed evidence of sophisticated metallurgy, materials, that could withstand the tremendous heat of combustion without warping or failure. The valve stems are chrome-plated, one of the metallurgists noted. Look at the surface finish. This isn't hand polishing. This is machine precision. Nakamura examined the combustion chamber. Its shape was carefully designed to promote efficient burning and high compression ratios. The spark plug location was optimal. Everything about the cylinder head design spoke to years of development and refinement. This wasn't a first-generation engine. This was a mature design that had been perfected through countless hours of testing and improvement. The specifications they'd extracted so far were remarkable. Bore, 5.75 inches. Stroke, 6 inches. Displacement per cylinder, 155.9 cubic inches. Multiply by 18 cylinders, and you got 2,804 cubic inches of total displacement, 46 litres. By comparison, the Nakajima Sake 12 engine powering the Zero displaced just 1,699 cubic inches, 27.9 litres across 14 cylinders. The American engine was 1.65 times larger in displacement, but it produced 2,000 horsepower compared to the Sake's 1,130 horsepower. That was 1.77 times more power. The Americans weren't just building bigger engines, they were extracting more power per litre of displacement. How? The answer emerged gradually as the disassembly continued. The crankshaft came out next, and several engineers gathered around it immediately. The shaft was a massive forging, machined to tolerances that Japanese manufacturing facilities struggled to achieve consistently. Nakamura ran his fingers along the bearing journals. The surface finish was mirror smooth, precise to within tolerances measured in 10,000ths of an inch. This requires specialized grinding equipment, he said quietly, and quality control, processes that can verify these tolerances reliably. One of the younger engineers spoke up. Could we build this, given time and resources? Nakamura didn't answer immediately. The question wasn't whether Japanese engineers understood the theory. They did. The question was whether Japanese industry possessed the machinery, the materials, and the manufacturing expertise to execute at this level, and do so not once, as a prototype, but thousands of times in production. The connecting rods told the same story. Each rod was forged from advanced alloy steel, then machined to final dimensions. The design incorporated features that reduced stress concentrations at critical points. The big end, where the rod attached to the crankshaft, used precision bearings that could handle the tremendous loads of high-power operation. The small end, connecting to the piston, was equally sophisticated. Look at this, Lieutenant Suzuki said, holding one of the rods up to the light. The I-beam, cross-section, is optimized for strength-to-weight ratio. They've removed material everywhere except where it's needed structurally. This isn't just good engineering. This is engineering backed by extensive stress analysis and testing. The pistons revealed even more sophistication. Each piston was an aluminum casting that incorporated cooling galleries designed to manage the tremendous heat generated by high compression ratios and aggressive ignition timing. Oil circulation through these galleries kept piston temperatures within safe limits, even under sustained high-power operation. Japanese pistons were simpler, lighter, more elegant in some ways, but they lacked these thermal management features, which meant Japanese engines had to run at lower power settings to avoid overheating and detonation. The Americans had solved the cooling problem, which allowed them to run higher compression and extract more power safely. As the days passed and the disassembly progressed deeper into the engine's internals, a disturbing picture emerged. Every component, every subassembly, Every design feature revealed manufacturing capabilities that Japan either didn't possess or couldn't execute at production scale. The precision forging of the crankshaft, the advanced metallurgy of the valve train, the sophisticated casting of pistons with internal galleries, the surface finishes that required specialized grinding and polishing equipment. Engineer Tanaka, who specialized in manufacturing processes, spent an entire afternoon examining the crankcase casting. He measured wall thicknesses, inspected the bearing boss machining, studied the mounting points for accessories. Finally, he looked up at Nakamura with an expression that combined professional admiration and strategic despair. "This represents a complete industrial ecosystem," Tanaka said. "The foundry that can cast this crankcase, the heat treatment facility that can process it properly, the machine shop that can bore and hone the bearing bores to these tolerances. The quality control systems that can verify everything meets specifications. And this is just one component. Multiply this by every part in the engine, then multiply by the production rate they're achieving." Nakamura nodded slowly. His notebook was filling with technical observations, but between the lines, an unavoidable conclusion was writing itself. Understanding the R2800's design was possible. Japanese engineers were perfectly capable of comprehending the engineering principles. But duplicating it, building it in quantity, powering their own fighters with equivalent engines, that was another matter entirely. Each component they examined revealed not just a design solution, but an entire industrial infrastructure Japan didn't have. And with American B-29 raids increasingly targeting what industrial capacity Japan did possess, the gap wasn't closing, it was widening. Of all the components in the R2800 Double Wasp, the supercharger system fascinated the power plant specialists most intensely. When they finally removed the supercharger assembly from the rear of the engine, they handled it with the reverence usually reserved for religious artifacts. Because this component, more than any other single piece of the engine, explained why American pilots could dominate combat in ways Japanese pilots could not. The supercharger was a two-speed, two-stage unit. That seemingly simple description concealed extraordinary complexity. Most Japanese engines used single-stage superchargers with fixed drive ratios. Simpler to manufacture, lighter. Adequate for low-altitude combat where most Pacific fighting occurred in the early years of the war. But adequate wasn't good enough anymore. The American system could maintain high manifold pressure across a wide range of altitudes. At sea level, the first stage compressed incoming air moderately, and the engine produced its rated power. As the aircraft climbed and ambient air pressure dropped, the system could shift to a higher drive ratio, spinning the impeller faster to maintain manifold pressure. At even higher altitudes, the second stage engaged, providing another compression stage that kept the engine breathing adequately even in thin air. The result? The Hellcat could fight effectively from sea level up to 20,000 feet and beyond. The Zero's Nakajima Sakai 12, with its simpler supercharger, was optimized for low to medium altitudes. Above 15,000 feet, its power dropped off noticeably. Above 20,000 feet, it was struggling. Lieutenant Commander Yoshida, who had specialized in engine development before the war, spent 3 days examining the supercharger components. The impellers were precision castings, balanced to tolerances that allowed them to spin at tremendous speeds without vibration. The drive gears showed sophisticated tooth profiles that minimized noise and wear. The intercooler system between stages cooled compressed air before it entered the second stage compression, increasing density and efficiency. This is precision machinery on a level we rarely achieve even in prototype engines, Yoshida reported. And they're producing this in quantity. Every Hellcat has this system, every Corsair, every late-model American fighter rolling off assembly lines. The tactical implications were devastating. Combat reports from the past year suddenly made perfect sense when viewed through the lens of the supercharger's capabilities. Japanese pilots had been reporting engagements where American fighters would climb above them effortlessly, hover at altitudes where Zeros struggled, then dive down with enormous energy advantages. Commander Nakajima, who had led fighter squadrons through 1943 and into 44, had submitted one particularly detailed report from an engagement over Rabaul. His unit had been flying combat air patrol at 12,000 feet when Hellcats appeared above them at 20,000 feet. The Japanese formation tried to climb to engage, but their Zeros couldn't match the Hellcats' climb rate at that altitude. The Sakai engines, starved for air, couldn't produce enough power. The American pilots had simply waited, maintaining their altitude advantage, then dove when they chose. Coming down with tremendous speed, they made firing passes through the Japanese formation and used their excess energy to zoom climb back to altitude before the Zeros could effectively counter. The Japanese pilots tried to follow them up, but their engines couldn't sustain the climb. They'd stall out short of the Hellcats' altitude, becoming easy targets in the process. They'd climb above us, Nakajima had written, then dive with energy advantage. We couldn't follow them up. We couldn't escape them coming down. They controlled when to engage and when to break off. We were helpless. That report, filed 6 months earlier, it had been disturbing. Now, with the supercharger disassembled on the workbench, it was simply documentation of predictable physics. The American engine could breathe at 20,000 feet. The Japanese engine couldn't. Everything else followed from that basic fact. The manufacturing requirements for the supercharger were sobering. The impeller housings were precision castings that required extensive machine work. The drive gears needed specialized cutting tools and heat treatment. The intercooler system demanded expertise in heat exchanger design and production. The control mechanisms that shifted between speeds and stages required sophisticated linkages and reliable actuation systems. Could we build this? One of the younger engineers asked. Yoshida considered the question carefully. Could we build one? Perhaps, given unlimited time and resources, our best craftsmen could probably hand-build a working prototype. But could we manufacture them in quantity, with consistent quality, while our factories are being bombed and our material supply lines are cut? The silence that followed answered the question more eloquently than words. Japan's engine manufacturers had been working on improved superchargers for years. The Nakajima Homare, which powered the Kawanishi Shiden, was supposed to deliver 1990 horsepower and competitive high-altitude performance. On paper, it looked promising. In reality, it was plagued with overheating problems, bearing failures, and inconsistent manufacturing quality. Pilots who flew Shiden fighters praised the airframe but cursed the engine. When it worked, it was competitive. But it frequently didn't work. The Mitsubishi Mk9, intended to power the next generation of Japanese fighters, had similar development problems. The supercharger was one of the primary trouble spots. Getting the drive mechanisms reliable, achieving proper cooling, maintaining adequate lubrication at high speeds, these challenges required manufacturing precision and quality control that Japan's bombed industrial base increasingly couldn't deliver. Engineer Tanaka examined the supercharger's bearings under magnification. The surface finish on these bearing races is extraordinary. Look at the uniformity. This requires precision grinding equipment and inspection tools that can verify tolerances to millionths of an inch. The Americans had those tools. They had the factories. They had the skilled workforce and the material supply chains. They had the testing facilities to refine designs through hundreds of hours of development running. They had the industrial ecosystem that made sophisticated supercharger production possible at scale. Japan had possessed some of those capabilities once, but by mid-1944, with B-29 raids intensifying and resource shortages crippling production, that ecosystem was collapsing. Understanding how the American supercharger worked didn't help if you couldn't manufacture the components to the necessary specifications. The supercharger represented, in one component, the entire reason Japan was losing the air war. Not because of courage or fighting spirit or tactical doctrine. Those things mattered, but they couldn't overcome the fundamental equation. American pilots could fight anywhere in the vertical dimension. Japanese pilots were increasingly confined to lower altitudes, where their engines could still breathe adequately. And in that three-dimensional battlespace, altitude was life. Altitude was energy. Altitude was the ability to choose when and where to fight. The Americans had it. The Japanese didn't. And this precisely machined assembly of impellers, housings, and drive gears explained exactly why. The fuel injection system seemed almost mundane compared to the supercharger's complexity. It was a collection of precisely machined components, fuel lines, metering units, and injector nozzles that delivered gasoline to each cylinder. But Lieutenant Commander Yoshida understood immediately that this seemingly simple system represented one of the most significant tactical advantages the R-2800 provided. Japanese engines, almost universally, used carburetors, float-type carburetors that mixed fuel and air through carefully calibrated passages and jets. They worked perfectly well in normal flight. Level flight, positive G maneuvers, climbing turns, any situation where gravity and acceleration kept fuel flowing properly through the float chambers. But they failed catastrophically during negative G maneuvers. Push the nose down hard, push into a dive where gravity pulls you up against your straps, and loose objects float weightless in the cockpit. In that moment of negative G, the carburetor's float chamber empties. Fuel stops flowing. The mixture goes lean. The engine coughs, sputters, and dies. Every Japanese pilot knew this limitation intimately. It had been drilled into them during training. If you needed to, dive away from an enemy fighter. You couldn't simply push the nose down. You had to roll inverted first, maintaining positive G throughout the maneuver, then pull back on the stick to execute what was technically a positive G maneuver from the pilot's perspective, but looked like a dive from outside the aircraft. That extra maneuver, that roll before the dive, took time, perhaps half a second, perhaps a full second if the pilot wasn't perfectly smooth. In a dogfight, where life and death were measured in fractions of seconds, that delay was often fatal. The Hellcat's fuel injection system eliminated this problem completely. Instead of relying on gravity and atmospheric pressure to deliver fuel through a carburetor, the injection system used a pump to force fuel directly to each cylinder through precisely calibrated injector nozzles. The pump didn't care about aircraft attitude. It didn't care about G-forces. Positive, negative, 0G, inverted, any attitude imaginable, the fuel kept flowing. An American pilot being pursued could simply push the nose down and dive. No roll required, no delay. Just instant transition from level flight to a dive that would quickly build to speeds where Japanese fighters couldn't follow safely. That half-second or full-second advantage meant American pilots could escape situations where Japanese pilots would be trapped. But the tactical implications ran deeper than just escape maneuvers. The injection system gave American pilots offensive options Japanese pilots didn't have. They could push over into attacks from above without worrying about engine cutout. They could execute complex aerobatic maneuvers without needing to maintain positive G throughout. They had complete freedom in the three-dimensional battle space, while Japanese pilots fought with one hand tied behind their backs. Combat reports filed throughout 1943 and 44 were filled with descriptions of Hellcats diving away impossibly fast, or pushing into attacks with aggression that seemed reckless until you understood their engines wouldn't quit. Japanese pilots, watching enemy fighters execute maneuvers that would starve their own engines, often assumed the Americans were simply better pilots, more skilled, more courageous. Now the engineers at Yokosuka understood the truth. The Americans weren't necessarily braver. They were simply flying aircraft with systems that allowed them to be aggressive without mechanical penalty. The fuel injection system's components sat on the examination bench, meticulously documented and measured. The injection pump was a precision assembly requiring machining tolerances Japanese manufacturing facilities struggled to achieve. The fuel metering unit incorporated complex passages and valves that had to be calibrated individually. The injector nozzles themselves were precision drilled, to deliver exactly the right amount of fuel to each cylinder. Could we retrofit our engines with injection systems? One of the younger engineers asked. Yoshida shook his head. Even if we had the manufacturing capacity, which we don't, the modification would require extensive redesign, and we'd need fuel pumps, which require electrical systems with adequate power generation. Our fighters would need heavier generators, larger batteries, more complex electrical systems. The weight penalty alone would be significant. The oil circulation system revealed similar American advantages through over-engineering. The R-2800's oil pump was larger than necessary by Japanese standards. Oil galleries through the crankshaft and connecting rods were generous. Bearing surfaces were oversized. Everything about the lubrication system screamed reliability margin. Japanese engines used smaller oil pumps, narrower galleries, tighter bearing clearances. These were conscious design choices driven by weight reduction priorities. Every pound saved in the oil system was a pound that could go toward fuel, capacity, or ammunition. But those savings came with a cost. Japanese engines ran closer to their lubrication limits, which meant they were more sensitive to oil quality issues, more prone to bearing failures, and less tolerant of sustained high-power operation. The cooling system told the same story. The R-2800 incorporated cooling passages that seemed almost wastefully large. Oil coolers with substantial surface area, intercoolers for the supercharger system. Everything designed to manage heat during sustained combat power operation. The engine's design philosophy became clear through these details. The R-2800 was built to produce 2,000 horsepower, not as a brief emergency setting that would risk engine damage, but as a sustainable combat power output that pilots could use continuously without fear of mechanical failure. The generous cooling, the robust lubrication, the oversized bearing surfaces, all of it created enormous reliability margins. Japanese engines were pushed to their absolute limits. Components were sized to minimum acceptable tolerances. Cooling systems were adequate for normal operation but marginal during sustained high-power settings. The engineering was excellent, the execution often brilliant, but the underlying philosophy prioritized performance per pound over reliability margins. The combat implications were brutal. American pilots trusted their engines completely. They could push the throttle to maximum power and hold it there throughout an engagement, confident the engine would keep running. Japanese pilots had to be more cautious, push too hard for too long, and the engine might overheat, seize, or fail in any number of ways. That caution, that need to nurse engines that were operating near their limits, meant Japanese pilots couldn't be as aggressive, even when tactical situations demanded it. Engineer Tanaka compiled a report on engine reliability, based on the examination of the Hellcat's power plant. His conclusion was damning. American pilots fly with the confidence that their engines will bring them home. Japanese pilots fly knowing their engines might fail them at any moment. This psychological difference is as significant as any performance advantage. The fuel injection system, the robust oil circulation, the generous cooling. Individually, these were engineering details. Collectively, they represented a design philosophy that valued pilot confidence and sustained combat capability over minimizing weight. And in the brutal arithmetic of air combat in 1944, that philosophy was winning. Not through any single overwhelming advantage, but through the accumulation of details that made American fighters reliable, their pilots confident, and their tactical options unrestricted. The Japanese engineers understood all of this now. They could see exactly how each system contributed to American air superiority. But understanding the problem didn't provide solutions when your industrial base was collapsing and your material supply lines were severed. Sometimes, knowledge just made defeat more visible. By early September of 1944, the captured Hellcat was ready to fly. The restoration team had worked for weeks, cannibalizing parts, fabricating components that couldn't be sourced, and carefully reassembling the fighter to flight-worthy condition. The NUR 2800 engine had received particular attention. Engineers wanted it running at full specifications to get accurate performance data. Commander Takahide Aoi walked slowly around the aircraft on the morning of the test flight. He was one of the Navy's most experienced test pilots, a man who had flown virtually every fighter in Japan's inventory. He'd been reading the engineering reports as the Hellcat disassembly progressed. The specifications were impressive on paper, but specifications didn't tell you what an aircraft felt like, how it responded to control inputs, how it behaved at the limits of its performance envelope. That's what test pilots were for. The cockpit felt cramped as Aoi settled into the seat. The Hellcat had been designed for larger American pilots, and even average-sized Japanese aviators found the space tight. But that minor discomfort vanished the moment he began the engine start sequence. The R2800 came to life with a sound unlike any Japanese engine. Not the high-pitched buzz of the Sakai, but a deep, thundering roar that spoke of tremendous power reserves. 18 cylinders firing in sequence, 2,000 horses pulling in synchronized mechanical fury. The entire airframe vibrated with barely contained energy. Aoi advanced the throttle for takeoff, and the acceleration was brutal by Japanese standards. The Hellcat weighed over 12,000 pounds at takeoff, significantly more than any fighter he'd flown, but the massive engine simply overwhelmed that mass with raw horsepower. The acceleration pressed him back into the seat with authority. The fighter rotated at 70 knots and climbed away from the runway at an angle that would be impossible for a Zero. Aoi noted the rate of climb immediately, 3,500 feet per minute at sea level, substantially better than anything in the Japanese inventory. The Zero could manage around 2,800 feet per minute when light and flown perfectly. The Hellcat did 3,500 feet per minute with fuel tanks full and ammunition loaded. Once airborne, Aoi began systematic testing. He climbed to 10,000 feet, leveled off, and began exploring the aircraft's handling characteristics. The controls were heavier than Japanese fighters. More force required to move the stick. Less immediate response to pilot input. The Hellcat felt solid, substantial, even a bit ponderous compared to the nimble Zero. But those heavy controls brought stability. Aoi pushed the nose down and accelerated. 200 knots, 250, 300. The Zero at these speeds would buffet violently, controls going mushy and unresponsive as airflow separated and shock waves formed over flying surfaces. The Hellcat just kept accelerating smoothly. 350 knots. 400 knots indicated airspeed. The controls remained effective. The airframe stayed solid. No buffeting, no tendency to pitch or roll unexpectedly. The massive structure that the engineers had documented, the heavy skin panels and robust internal framing, absorbed stresses that would tear lighter aircraft apart. Aoi pulled back on the stick, converting speed into altitude in a zoom climb. The Hellcat shot upward, carrying its tremendous momentum skyward. He held the climb until the airspeed bled off, then pushed over and dove again. This was the fundamental tactic American pilots used: boom and zoom. Dive from altitude with speed advantage, make a firing pass, then use excess energy to climb back to altitude before the enemy could react. A Zero pilot trying to follow that dive would face an impossible choice. Follow the dive and risk structural failure at high speeds, or break off the pursuit and watch the American escape. Either way, the American pilot controlled the engagement terms. Aoi climbed to 15,000 feet and requested a training Zero from the base to join him for comparative flight testing. When the Zero arrived, they began a series of mock combat engagements. In a slow-speed turning fight, the Zero could outturn the Hellcat easily. Tighter radius, better rate of turn, more maneuverable in every traditional sense. But Aoi simply refused to fight that way. He used speed and vertical maneuvers to dictate engagement terms. He'd dive from above with a speed advantage, make a mock firing pass, then zoom climb back to altitude using the R2800's superior power-to-weight ratio at high speeds. The Zero pilot tried to follow vertically and lost speed rapidly. The Hellcat kept climbing on sheer power, putting distance between them until the Zero stalled and had to pitch over. In that moment, the Zero became an easy target. Aoi tried various approach angles and attack geometries. Every scenario played out the same way. As long as he maintained speed and used vertical maneuvers, he was untouchable. The power advantage the R2800 provided translated into tactical invincibility when flown properly. After landing, Aoi spent 2 hours writing his detailed test report. His conclusion was succinct but devastating. The F6F Hellcat represents a fundamental shift in fighter combat philosophy. The aircraft's performance is not built on maneuverability, but on power management and vertical tactics. The engine makes everything else possible: the speed to engage or disengage at will, the climb rate to maintain altitude advantage, the ability to absorb battle damage through robust construction that weight would prohibit in lighter aircraft. He paused in his writing, then added a final observation. Our pilots are not being outflown, they are being outpowered. The R2800 engine gives American pilots tactical options we simply do not have. No amount of training or fighting spirit can overcome the fundamental equation of 2,000 horsepower against 1,100. The test flight had confirmed everything the engineering examination had revealed. The engine was the key. The 2,800 Double Wasp made the Hellcat's tactics possible. It enabled the robust construction that kept pilots alive. It provided the climb rate that maintained altitude advantage. It delivered the power that let American pilots escape any situation by simply diving away. Japanese engineers and pilots now understood exactly what they were fighting. They understood why combat reports had been so consistently grim. They understood why pilots were dying in such appalling numbers. But understanding the enemy's advantages didn't help when you couldn't match them. The R2800 represented industrial capabilities Japan didn't possess. And as Aoi walked away from the captured Hellcat that September afternoon, he understood that all the courage and skill in the world couldn't overcome 2,000 American horsepower thundering through Pacific skies. The engine made everything else possible: the tactics, the survivability, the victory. And Japan had no answer for it. In late 1944, Japanese engineers studied the American R2800 engine and concluded it was impossible to replicate. Japan lacked the steel, precision machinery, and industrial infrastructure America had spent decades building. Engines like Nakajima's Homar failed from poor materials and quality control. They understood the Double Wasp, but couldn't build it. By late 1944, Japan understood it was losing the air war. American industry produced overwhelming horsepower, millions more than Japan could match. The captured Hellcat's R2800 engine symbolized the gap, flawless engineering born of vast resources. Japan's understanding was complete, but its means to act were gone. Defeat was inevitable. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.